Hello everyone, this is Professor Roman. Welcome to the 48th video in my video lecture series, An Introduction to Discrete Mathematics. Well, we're now ready to discuss the Huffman codes. And the Huffman encoding scheme, as we will see, has the smallest average code word length, or smallest weight if you prefer, among all instantaneous encoding schemes for the same source. And since we always want encoding schemes to be instantaneous, essentially that means that the Huffman encoding scheme is the most efficient, period, in terms of average code word length. This encoding scheme was discovered by David Huffman when he was a doctoral student at MIT in the 1950s. To describe Huffman's code and the encoding scheme, we're going to use a tree, which is naturally enough called a Huffman tree. And so let me illustrate the procedure with a source alphabet here and its table of frequencies. It seems somewhat more common to use frequencies rather than probabilities for the Huffman encoding scheme, but it doesn't matter. You can use either one. The algorithm, the Huffman algorithm, creates a tree whose vertices lie on different levels. At step one, we place one vertex on the top level for each character in the source alphabet. We label the vertices with that character as well as with their frequencies. In the next step, we take the two vertices on the left, those are the ones with the smallest frequencies, and we combine them as leaves of a little tree. And so the top vertex is a new vertex. We insert it top level, and we label it with the sum of the two frequencies. And basically what we do from then on is the same thing over and over again. We'll rearrange the top level nodes in increasing order of frequencies. I hope I said that here. Step one, these are listed in increasing order of frequencies. So we rearrange again if necessary. Now you'll notice here that two of the top level frequencies are equal. We could order these in either way. Put either one of these first, it doesn't matter. So this tells you right off here that the Huffman algorithm is not unique and Huffman encoding schemes are not unique. But either way we do this, any way we do this, it will produce an encoding scheme with the smallest average code word length, so it doesn't matter, at least from that perspective. Now we do another combining of these two vertices, and that will look like this. So we take B and the vertex labeled 9, and we drop those down, connect them with the top level vertex, and label it with the sum 7 plus 9, 16. Another rearrangement on the top level, another combining, another rearrangement, which is, let's see, we did, okay, these are already in the correct order of frequency, so we don't have to do a rearrangement. We just do another combining of these two. That brings us to here. Frequency is now 25 plus 25 is 50. Now we have to rearrange the top level and do a final combination until we're down to a single vertex at the top level. And the final step, once we get here, is to we can remove all the frequencies. They're no longer needed. And label the edges. Edges that have a positive slope get labeled with a 0. Edges that have a negative slope get labeled with a 1. And we have what is called a Huffman tree. To find the code word for a particular character, all we have to do is start at the top and follow the path to that character. So for example, for the character B, we start here and follow the path. So the code word will be 1, 0, 1, 0. For C, it'll be 1, 0, 0. And here's a list of the Huffman code words and the encoding function at the same time in this table. Frequencies are no longer necessary. I don't know why I put them in there, but I did. It's useful information to have if you're encoding messages, I suppose. Now, as you can see from at least this example, the Huffman code has the prefix property. Also, characters with higher frequencies, such as 32 and 25, have the shortest code words. And I computed the weight of this particular encoding scheme, although, as we've discussed before, the number 182 by itself means nothing. It only becomes meaningful when you compare it to the weight of some other code to see which is larger. So officially, a Huffman encoding scheme is an ordered quadruple. You have the source alphabet, the probability, the set of code words, otherwise known as the code, and the encoding function. So in this case, we have our source alphabet. Our probability distributions come from the frequencies by dividing by the sum of all the frequencies, which I think is 82. The Huffman code itself is just the code words in this final column. And the encoding function you read by going across the rows. So that is the Huffman encoding scheme for this particular example. A couple of comments about the Huffman algorithm and the Huffman encoding scheme. As I mentioned, there is in general some leeway in this algorithm. In particular, when two top-level nodes have the same frequency, you have some leeway in how you order those top-level nodes. So there can very likely be more than one Huffman encoding scheme for a given source. But as I said, all of them have the smallest average code word length. Another fact that's apparent from the algorithm at step 2, in fact, is that these two characters, which are characters of the smallest frequency, or frequencies, could be different frequencies, 4 and 5 in this case, they will end up in the tree as siblings, and they have the same parent. So the code words will be what I called siblings. The code words will be the same length and will be identical except in their last bit. These are the two characters I'm talking about. When you get to this point here, you followed the same path. So you built the same code word up to that point. Then one of them gets a 0 attached, the other gets a 1. So we got sibling code words down here. If you look at, these two code words, they're identical until you hit the last bit. Now this should remind you of something we did in the previous video, where we started with any instantaneous encoding scheme, and we were able to tweak it so that the last two code words, CQ-1 and CQ, were sibling code words. We don't have to do any tweaking. The Huffman algorithm does it for us. And this will be instrumental in proving that the Huffman encoding schemes produce the smallest average code word length. As to the prefix property, we saw in the example that the code has the prefix property. In general, it does, and that's quite easy to see from the tree itself. If a code word C was a prefix of another code word D, then when we traverse the Huffman tree from the top vertex to the vertex labeled D, we would have to come first to the vertex labeled C. That's the only way C could be a prefix of D. But the labeled vertices are the leaves. Any path from the top to a leaf does not go through another leaf. It can't. Leaves have degree 1. You go in, you can't come out. So it's a very simple argument looking at the Huffman tree, because the code words, the code words and the characters lie only on the leaves. No code word can be a prefix of another code word. Now, showing that Huffman encoding schemes have the smallest average code word length among all instantaneous encoding schemes for the same information source, well, this is a bit delicate, and it's going to take a bit of work. So let's get started. Here's the theorem. The Huffman encoding scheme, script H, has the smallest average code word length among all instantaneous encoding schemes, script C, for the same information source. Same source alphabet, same probabilities. And for the proof of this, which is a bit long, here is the notation. It's the same notation that we used earlier for the code C. We have our source symbols and our probabilities, and here are the code words for the random, arbitrary, instantaneous encoding scheme C, and here are the Huffman code words and their lengths. Okay, so that's our notation. And what we need to show is that the average code word length of H is less than or equal to the average code word length of C. And we can assume that C has been what I call normalized. It's my own term, not standard, because that does not increase the average code word length. So if we can show this inequality holds for a normalized instantaneous encoding scheme, we know it holds for all instantaneous encoding schemes. So these are the facts that we have to work with. The probabilities are organized in this way. The code word lengths for C have this property. The last two code words in C are siblings. And as we've just discussed, the last two code words for the Huffman code are also siblings. So I've written them here. So this is what we have to work with, because we've normalized C and because we've already made this remark about the Huffman codes. Here's the theorem again. I just restated it so we can begin the proof. Now this particular proof is by induction on the size of the source alphabet, which is Q. So I'll go back here a second. Where is the source alphabet? Here it is, S1 through SQ. Induction is a terrific proof technique. Sometimes it seems to be the only reasonable way to go. I don't know if there's a non-inductive proof for this or not. The problem with inductive proofs is that they often, well, make it more difficult to see what is really going on, what the real property is that makes the proof work. But this is what we have. Now for Q equals 2, the average, the Huffman encoding scheme has average code word length 1. We just have two code words, 0 and 1, and we can't get any smaller than that, so the result is true for Q equals 2. That's our basis step. So we'll assume that the result is true for all source alphabets of size Q minus 1, and suppose that our source alphabet has size Q. Well, for the purposes of induction, what we need to, in order to apply the inductive hypothesis, are encoding schemes with one less source symbol. So they have size Q minus 1, and we can use the inductive hypothesis. So how to do that? Well, we can do the obvious, and that is delete the last source symbol to get the source S prime, which is little s1 through little sq minus 1. We don't know this is going to work. Actually, you do, because you know the proof is going to work. But initially, we don't know if it's going to work, but it's the obvious thing to try. Well, we've got to fix the probability distribution as well. And we can't just lop off the last probability, because remember, the probabilities have to be non-negative and sum to 1. So what we need to do then, if we lop off p sub q, is to adjust p sub q minus 1 to, you might say, take up the slack. So we're going to replace p sub q minus 1 by p sub q minus 1 prime, which is the sum of the original pq minus 1 and pq. So we still have a probability distribution. So we have a new source, a new information source, S prime, P prime, and S prime has size Q minus 1. Now what about the code and the encoding function, both from H and from C? We need to extract from them encoding functions codes and encoding functions that will fit this shorter information source, S prime, P prime. The changes that we can make to accomplish this are the same in H as they are in C. So rather than go through both, do the same thing twice, let's do it for C, and you'll see that it would work just as well for H. So from C, we need to define another encoding scheme, C prime, for the new source, S prime, P prime. Well, the last two code words in C are siblings, and that's the key. And this is also true for the Huffman encoding scheme. The last two code words are siblings. And in fact, this is exactly why I went through the trouble of this discussion of normalization, so that I could normalize C and its two last code words would be siblings. So what we can do, here are the two code words. They're identical, same length, identical except in the last bit. We can replace both of these code words with the common prefix of the two code words. Now, that produces a new code. So I've got C prime Q minus 1. That's the common prefix. CQ is gone. So is the original CQ minus 1 being replaced by this. But we have to check some things about this. It's a set of code words, but we have to make sure there's no duplicates, and we need it to still have the prefix properties so that the associated encoding scheme has the prefix property. Okay. So does C prime have the prefix property? Well, since the new code word, CQ minus 1 prime, is a prefix of the original code words CQ minus 1 and CQ, and the original code C had the prefix property, this prefix was not a code word in C, so it's not a code word in C prime. That's to say, it's not one of these other code words in C prime. So, in short, CQ minus 1 prime is a new code word. Also, CQ minus 1 prime is not a prefix of any of these other code words. Okay. Because it's too long, basically. There are only two code words for which it is a prefix, and those are these two code words which are gone. So C prime does indeed have Q minus 1 distinct code words, and it has the prefix property. Now I expect you will want to go over what I just said a couple times until it seems reasonable. It wouldn't be surprising if all that sounded like gobbledygook. Okay, so it takes a while to absorb this, no question. As far as the encoding itself, the encoding function, we will encode all the source symbols up through up through SQ minus 1, SQ minus 2, the same way we did before. That doesn't change. The question is, what do we do with the new code word? And we will use the new code word to encode SQ minus 1 which is the same symbol we had before, but it's got a different probability now. So we have defined our shorter source, information source, S prime P prime. We have modified the instantaneous encoding scheme C to a new encoding scheme C prime. Here is the new code. It's one shorter than the original code to match what we did to the source alphabet. And here is the encoding scheme. We can do exactly the same thing with the Huffman encoding scheme. The source is the same. We reduced it. It's the same for both schemes. So the character set and the probabilities are the same. That's taken care of. But if you remember, the last two Huffman code words are siblings. So you can just put an H here for the C's and put Y's here for the X's and do the same thing over here. It's the same process. So the new code looks very much like this one. And the same thing for the encoding source. So it wouldn't be a bad idea to pause and do that yourself for the Huffman encoding scheme. You will end up with two new encoding schemes, C prime and H prime. These are the information sources. The information source is only one, and I've recopied it from earlier. And here is the code and the encoding function for C. Here is the code and the encoding function for H. Now let's remember why we did all this. We want to apply the inductive hypothesis, so we needed encoding schemes whose source alphabet had size q-1. And we have done that by tweaking both C and H, script C and script H. Now, as far as applying the inductive hypothesis, the encoding scheme C prime is just fine for the inductive hypothesis. And that's because C prime is instantaneous and its average code word length is no longer than that of C. And I'm going to leave that for you to think about until it seems clear to you. But we have an issue regarding the new scheme H prime. Remember that the setup is that H or H prime has to be a Huffman encoding scheme. H is assumed to be a Huffman encoding scheme, but we can't use the inductive hypothesis unless we show that H prime is also a Huffman encoding scheme. It's an encoding scheme. But how do we know it's a Huffman encoding scheme? How do we know that the Huffman algorithm applied to the new source S prime P prime can produce the code H prime with encoding scheme little h prime? That's a bit of a subtle point. I mean, it's a critical point, but I can see how it could easily be overlooked by someone who wasn't, what should one say, quite as circumspect as required here in this proof. Okay. To put it a little more bluntly, which I can do here, give me some space. This is what we wish to say is true because of the inductive hypothesis. that the average code-word length of H prime is less than or equal to the average code-word length of C prime. But in order to make that conclusion, C prime is fine, it's an instantaneous encoding scheme, but H prime must be a Huffman encoding scheme. And while it turns out it is, that's not so easy to show. So here's what I did to try to show that that H prime is a Huffman encoding scheme. Let's go back to the Huffman algorithm that produces H, script H, the original Huffman encoding scheme on the full source alphabet. So step one, we line up the vertices here and we label them with the source symbols, and I'm using the probabilities now, and PQ is the smallest probability. Remember, the probabilities descend from P1 down to PQ, and here's PQ minus 1 and so on. And the next step is to combine these two vertices, and I've drawn everything in red here. And we label this top node with the sum of the two probabilities, PQ plus PQ minus 1. And here is the final, at step K, is the final Huffman tree. I've already switched over to where I dropped most of the frequencies because I didn't feel like figuring out labels for all these vertices. It's not important. And I've added the bits to find the actual code words. But I left these two vertices labeled. Okay, so I would remove these two vertices. The two probabilities, and I'd be done here. And I didn't put, in these other leaves, I didn't put the characters because it's not important. Now, this is the previous step. Now, I've inserted here a new step that's not technically part of the Huffman algorithm. And what I did here, I didn't touch anything except this first location here. And I replaced all the stuff in red by a new vertex, and just for emphasis, I made it gray, with the single source SQ minus 1. So SQ's kind of disappeared here for now. This is, as I say, not officially part of the Huffman algorithm. However, the point is that once this initial little mini tree is created in step 2 in any Huffman algorithm, all that matters for the rest of the steps is the top vertex and its probability or frequency, because the rest of it just goes along for the ride all the way through the algorithm. You just keep recopying it. You don't change it. You don't even look at it. You don't care what PQ and PQ minus 1 are. All you care about is what the sum is. So you may as well save some ink and some space and just use a single symbol and a single vertex representing the top vertex. In fact, once that gets combined, it drops down. Even that vertex from that point on is of no importance until the end, of course. So I inserted this step 3, and the point is it's not going to affect the rest of the algorithm because this stuff isn't on the top level anymore. So when I get to the end of the algorithm with the replacement, that would be step k minus 1, this vertex will end up a leaf somewhere down the tree. Then if I replace this sort of substitute vertex with the original tree that I took out, I will get the final Huffman tree. So this is the tree that defines script H. But what if I just started at step 3 and went through step k minus 1? That is a Huffman algorithm. It's perfectly acceptable to start the algorithm right here. It's for a different source alphabet, namely SQ minus 1, SQ minus 2 down to S1. In other words, SQ is missing. Well, that's exactly what we did here. We took away SQ. And if we just go from step 3 to step k minus 1, it's also for a different probability distribution, because the first probability here is PQ plus PQ minus 1. Well, that's exactly what we've got here. Okay. And so what about the code that we get if we just go from step 3 to step k minus 1? What can we say about that? Well, perhaps nothing directly. I mean, maybe we can, but it's easier to look at this one. This is the final Huffman tree for H, not H prime, for H. The code words down here are siblings. They look like, well, the H version of these two. They're the same length, and they're the same except in the last bits. And for H prime, they would get replaced by this version, the H version. So this would be H, Q minus 1 prime, and so on. So that's the code word that goes with this SQ minus 1 here. But this vertex gets the code word that you would get by taking these two code words and chopping off the last bit, backing up to here, which is what this is. So what I'm saying basically is that if we shorten the Huffman algorithm to start at step 3 and end at step k minus 1, we still have a Huffman algorithm, but it is for this source alphabet with these probabilities and with these code words and with this encoding function. So H prime, script H prime, is a Huffman encoding scheme. Well, I know that was a fairly intricate argument. May have to, rewind a little bit. To be honest with you, this is about the 5th version of this argument that I wrote up. I didn't like the first 4. I kept changing it because it's not really that complicated, but it's rather difficult to explain. Okay. But I hope at the very least you see the purpose, and that is we did need to make sure that this wasn't just any old encoding scheme, but it was an encoding scheme you get from a Huffman algorithm. So now we need to turn our attention to the average code word lengths. We have now 4 encoding schemes: H and H prime, C and C prime. And we can now apply the inductive hypothesis to H prime and C prime, but we need then to translate that fact up to H and C. So we need some information about the average code word lengths for all 4 of the encoding schemes. Or actually what we need is to relate the average code word length of H and H prime, and also of C and C prime. So just as I was speaking, I realized I should have added this, just to be clear. Now that we know that H prime is a Huffman encoding scheme, we can invoke the inductive hypothesis and conclude that the average code word length of H prime is less than or equal to the average code word length of C prime. Now, we're still trying to show the average code word length of H is less than or equal to the average code word length of C without the primes, so we need to relate the average code word lengths. Well, the average code word length of H prime can be obtained from the average code word length of H. And you can see that here. The average code word length of H is going to come from this tree, and we have these 2 code words, and their length is 1 greater than the length of the path to its parent, to the parent vertex. And so to get to the average code word length of H prime, that's going to be from this tree. We need this now. This vertex now represents a code word, so we need its path length. So we give up these 2 path lengths, but acquire this path length. So the way I put it, quite simply, is the average code word length of H prime can be obtained from that of H by subtracting the contribution of the small red tree and adding the contribution of this vertex. So the small red tree's contribution is the length times the probability for SQ minus 1 plus the length times probability for SQ. And remember, these 2 lengths are the same, but I left it this way for clarity. And then we add the contribution of the leaf labeled SQ minus 1 over here. Okay. So what is this weight? The length of that code word is 1 less than the length of the original SQ minus 1 before we tampered with the source alphabet. And that vertex has probability equal to the sum. So this is what we add. We subtract this and we add this. So the average code word length of H prime equals the average code word length of H minus this quantity plus this quantity. And because the 2 last code words in the Huffman encoding scheme and in the other one have the same length, there's a lot of collapse. And the average code word length of H prime is equal to the average code word length of H minus the sum of the 2 probabilities. These are the smallest probabilities. So the lengths of the code words have disappeared. Okay. And that's absolutely critical, because when we do the same thing, mutatis mutandis, that's one of my favorite Latin terms. It means with the necessary changes. We switch over from H to C. Those last code words also have the same length, and we get a very similar computation that leads to the same relationship between the average code word length of C prime and that of C. Well, now, at long last, we are almost done, because this relationship and because these two relationships, we get the average code word length of H is the average code word length of H prime plus this sum, because we've got to move it to the other side. And that's less than or equal to the average code word length of C prime plus that same probability. And that's equal to the average code word length of C. And we're done. Well, I hope that wasn't too challenging. It certainly may take a few reviews of this explanation to get comfortable with it. That's what I would expect. Frankly, it took me a few times to get comfortable with it. So don't feel discouraged. Well, we have completed our discussion of Huffman codes and binary search trees. What's next? Undirected networks and the minimum spanning tree problem. So thank you for watching, and I hope to see you in the next video.